So good morning all. So last class we have discussed about the envelope detection and what are the factors plays a vital role in order to identify the envelope of a particular input signal. If the input signal, last class also we have discussed that if the input signal, if it is a sinusoid or if the input signal, if it is a cosine signal, the output of this particular envelope detection is going to be a DC output. Why? Because here we are using a nonlinear element that is called a diode, and the diode will rectify only the positive half component, and due to the presence of this R and C, this discharging and charging plays a vital role. This thing already I have explained. Once again I will explain it for the continuation what I will do today. So first here you can see that input is provided to our envelope detector. In the envelope detector means the diode is followed by an RL with respect to C. RL means load resistance and C. So this particular filter is act as a smoothing filter also. Okay. So now how it works? It is a simple to design. So when the input signal is provided, the current will flow and crosses through this capacitor. So when it is switched on, that means it becomes a short circuited. At that particular time, the capacitor will charge up to the input potential. Now, input potential we have provided that it is a sinusoid signal. Peak amplitude is plus A to minus A, and this is the two complete cycle we are identifying. But when this particular sinusoid signal is provided to this diode, it will rectify only the positive half, because the diode will operate in a forward biased condition. So if it is a forward biased condition, then the positive half of a particular cycle will be identified first, then next half cycle will be identified. Okay. Now the thing is, first if the input is provided, if the input is provided with respect to this diode with a small potential, let us consider the time is t is equals to 0 plus. As I have written, t is equals to 0 plus means there is a small change or there is a small increment of a potential. So if there is a small increment of a potential for a time period 0 plus, your P must be greater than N. That means it enters to the forward biased condition. If it is entered to the forward biased condition, this diode will act as short circuit. So current will flow in this particular condition. Okay. Now once the diode is short circuited, now once this capacitor is getting charged, so that means when it is switched on for this particular time period, your capacitor output will have the same potential what I am providing. For example, I am providing, in this figure you can see, I am providing the potential of 0.01 volt. Okay. So the same potential will be available at the output, that is Vc of t. Vc of t means it is a voltage across this. V0 of t is same as Vc of t. So this Vc of t will have the same potential. So it is having the same potential. Similarly, when it reaches to the peak potential, when your input potential Vi of t reaches to the peak potential A, your Vc of t is also having the same potential A. Now the question comes, when it is coming down, that means when the potential decreases, what happens? When the potential decreases, your forward biased condition will turn off to the reversed biased condition. But there is some conditions are there, due to which for this complete cycle, only first half or the positive half is going to be rectified, for negative component also. So our diode will work in this particular point up to this much. This is the crossover point. So the diode, if there is only R is there, that means only this particular half will be generated. But due to the presence of this capacitor, what happens? When it is charged, it will start discharging. Okay. When it is start discharging, that means it will act as open circuit, and the discharging will take place in this particular loop. Here you can see that when it is an open circuit, that means when the diode is in reversed bias condition, the capacitor start discharging. And the capacitor start discharging means again it come into picture, that time constant. Now last class I have discussed the time constant tau is equals to RL into C. Now this time constant plays a vital role to form an envelope. Okay. Now this tau is equals to RL into C. So it depends upon the time constant, means the time how much it is fast or it is slow. If the discharging rate is fast means the time period is less. Rate means it is a frequency component. Okay, two things it will come into picture: if the discharging rate is fast or the discharging rate is slow. If the discharging rate is fast, that means your tau RC into L is small, so the time period for the discharging is less. Similarly, if the tau is equals to RC into L is high, that means rate is less. If this is small, rate is going to be high. Due to the presence of this time constant, the RC component will identify the next potential or the next peak. So here the negative potential won't be identified with respect to this diode, because diode operate in a forward bias condition. So again it will identify the next positive half cycle, and then again it start. This is called as a discharging, this is called as a charging. Okay, so during the discharging it will again identify the peak value of next cycle and again start discharging. So this is the charging point and this is the discharging point. Same thing I have written here. So what will be my actual output? The actual output will be, since I have provided the DC component sine wave, so my DC component will be, first this is charging, then this is discharging, then this is charging, then it is discharging. Now this particular time period, discharging rate, it plays a vital role. If your discharging rate is small, so that means time period is very high. So discharging rate will be small. If the discharging rate is high, your time period is very small. In this case I can say the discharging time period is high, so that rate is less. But similarly, if I will draw a diagram like this, so here, if you compare these two figures, in this case the time period is high, that means rate is less. So time period is high means your tau is equals to RC into L is high. So if this component is high, means frequency component is less. So in this case you can see the time period is high, frequency component is less. Next, in this figure you can see that when it is charging and discharging, here discharging time period is less. So discharging time period means tau is equals to RL into C. If it is less, that means your frequency is going to be high. So if the frequency is going to be high, that means the discharging rate is high and the time period is less. Why I am discussing these two figures? Because this envelope detector is going to demodulate your received AM signal. As we know that AM signal is consist of two components. One is carrier and one is modulating signal. Now amplitude may deteriorate, but frequency cannot be deteriorated. Okay, so what he will do, he will identify, this circuit will identify two frequencies, one the low frequency, one the higher frequency. If it is low frequency, that means it will correlate with respect to the modulating frequency, and if it is a high frequency, it will correlate with respect to the carrier frequency. Okay, so last class I have written that 1 by Fc less than RL into C, very less than 1 by Fm. So this is the condition or the time constant which plays a vital role. Your tau of this particular circuit, tau means RL into C. This RL into C plays a vital role in order to identify the modulating signal and identify the carrier component. That we will see step by step. Okay. So the condition is what? Your RL into C must be very greater than carrier frequency. Then only the envelope will identify. And this RL into C is less than 1 by Fm. So this condition must be satisfied. If this condition is satisfied, that means easily we can identify the envelopes. Okay, and that envelope plays a vital role through which we can extract our modulating signal. So this is the first case. Now second case, at t is equals to t1 means at t is equals to t1 means it is a peak value. Okay, so at peak value what happens? The input reaches to the maximum value and the output is also reaches to the maximum value. That means input is equals to A and Vc of t is also equals to A. So this is the maximum output we are getting at t is equals to 1. After getting this maximum point, again it comes down to the negative half cycle. So our diode will be in forward biased, but since the potential is decreasing, at the same time the diode will act as an open circuit and your capacitor will act as a source and it will start discharge. If it is start discharge, then this particular circuit plays a vital role. Now discharging time period depends whether it will correlate with respect to low frequency or whether it will correlate with respect to high frequency. So if the time constant is high, that means if the discharging time period is more, that means your frequency is going to be less. Similarly, if your discharging time period is low, that means the frequency is going to be high. These are the two figures which I have shown. Here you can see the discharging time period is high, so that means frequency is going to be less. Now what is the effect we will discuss now. Similarly, if the frequency is high, that means your time period is less. So discharging time period is less. Now we have to maintain this time constant between the carrier frequency and modulating frequency in order to extract the modulating signal. For that, the three cases we will see when Tc is high and this is low. If the time constant is high, what happens? If time constant is low, what happens? And how we will recover the original modulating signal. Okay, so one by one we will discuss. So this is the condition for proper envelope detection. This is the condition for proper envelope detection. Now the cases we will see how this detection will help us to generate the modulating signal from the envelope detector. Okay. So first case 1, the condition is RC is very less than 1 by FC. Okay. In this case, your RL into C is too small. RL into C is too small means time constant is small. If time constant is small means frequency is high. Okay. So that means your frequency is high. If I will relate this one, 1 by F is very less than Fc, or I can write Fc is very less than F. So this is the condition, and this F is equals to 1 by RL into C. This is the 1 by tau relation, or this you can write 1 by tau. Okay, where tau is equals to RL into C and Fc is less than this component. So this is RL into C is too small. That means time constant is too small. So first case is if the time constant is too small, your frequency is going to be very high. So if it is going to very high, what will happen to my output signal? Okay, that we will see. So first, now suppose if the AM modulated signal we have inserted to this particular value or this particular envelope detection. Here we have provided the sinusoidal signal. So my output look like this. Similarly, if the input is my AM signal, then how to reconstruct the original signal? Original signal means message component. That means, so let us consider the input to the envelope detector is this is the AM signal. When we will get this one as an AM signal? S suffix AM of the when your modulation index is less than 1. This is the condition. Okay. So this is your AM signal MA less than 1. Let us consider this is the input to my envelope detector. Now as the diode is present, it will only rectify the upper half, means only positive half it will rectify. Negative half it won't rectify, because negative half it will be in a reversed bias condition. So what I will do, the output of envelope detection means V naught of T. So now how it is going to be represented, that we will see. So first is this, then second is this, third is this, fourth, fifth, sixth, seventh, like this. Negative half component were suppressed because it is a reversed bias condition. When the negative cycle will come, your diode will act as an off, so it will only rectify the positive half signal. Now if it is rectifying positive half signal, then how we are going to decide this RL into C? This RL into C will identify the peak value and then discharge it, identify next peak value and then discharge it. Now next it will identify like this, discharge it. This yellow line you can see, these are discharging and charging lines. So first it will identify the peak value moving to the peak value, then it starts discharge until the next peak value comes. Then again it starts discharge, again it reaches to the peak value of third loop. Similarly, this yellow line is called as an envelope. Okay. Now if this envelope is done, if it is very small, okay, if the time constant is RC component is too small. If RC component is too small means it will take higher frequency component and you will get the maximum point over here. So this is the value, means this is the particular time period through which it will identify the discharging time period. Actual envelope you will get in this particular yellow line, but since your RC into L, if it is too small, that means your frequency is going to be high. If the frequency is going to be high, that means it won't come in this particular point, it will directly come to this next part. So this is the time period, it is for high time period, this is for low time period. So discharging time period is less, that means the frequency component is high and it will continue with respect to this envelope. This is the first case. If your RL into C is too small, that means frequency is very high. So this is the case when the frequency is going to be high. Now when this frequency is going to be high, we need to control it. We need to means it need to be within a particular limit. We cannot exceed that limit. What is that? It must be greater than Fc. So if it is less than Fc, then it will come down and the diagonal element will come. So if it is come down, my output will look like this. My output will look like this. So that means like this value it will come. Like this. So this won't be my original message signal. This won't be my original message signal which I am extracting with the help of an envelope. My envelope is this one. But since due to the increase in time period or due to the less in time period, okay, your frequency is very high. If the frequency is very high, your output will look like this particular output of an envelope and it is in a sawtooth. okay, and this sawtooth does not convey any sort of information, okay. So due to this, we have to maintain that particular frequency, and that particular frequency is 1 by fc. So it must not less than 1 by fc. So here you can see the relation that RC component is very less than 1 by fc. That means fc must be very less than f. So here the output signal what we are designing, this time constant plays a vital role. If this is too small, then the frequency is going to be high with respect to carrier frequency. We have to maintain it. Always, if the carrier frequency is 100 Hz, your tau must be, or this RC frequency must be 200 Hz. Then only the proper envelope detection can be done. So this is the case what we will identify for if RC is too small. Similarly, we will see for second case if RC is too high. Okay. One minute. Now, case 2. Case 2 indicates that your time constant RL into C is very greater than 1 by Fm. Now, if it is very greater than 1 by Fm, this indicates what? This indicates that the frequency which is available at RL or this tau is equals to RL into C. Now for this, I will write F is equals to 1 by tau. Okay. So here I can write in place of RLC 1 by F is greater than Fm. 1 by Fm. So here I can write Fm must be very greater than F. Then only the original message signal can be recovered. This is the condition for second. We have to limit the two frequency, or we have to limit our this time constant between Fc and RL. Now here you can see with respect to the carrier frequency. Here we will see with respect to the modulating frequency. Now here again, this is the output of diode, and this is the envelope. Let us consider like this. And these are the positive half of an AM signal. Positive half of an AM signal. Then, now, here, how we will identify the modulating frequency? The modulating frequency is correlated with respect to this frequency. Your modulating frequency must be very greater than F. Now in this case, RL into C is very greater than 1 by Fm. Now if it is very greater than 1 by Fm, that means the time period is more with respect to the modulating frequency. If the time period of the discharging capacity is more, your frequency is going to be less. So here what happens? In this sort of case, here RL into C is too high. If RL into C is too high, that means your frequency is less. Okay? If the frequency is less, the discharging time period is going to be high. If the discharging time period is going to be high, we will get this sort of output. Peak to peak. Then it will come here. Then maximum. Then directly here. Then maximum and then minimum. So this is the case what we are going to identify at the output of the envelope detector. 1 minute. draw it once again. So this is the positive half. This is the first lobe, like this. Okay, so this is the positive half of an AM signal, that is V naught of t. Now in this case, when your time constant is high, your frequency is going to be less. So in this case, what will happen? It start charge, then discharge, then charge, then discharge, then charge, then discharge, then charge. Again it is discharge. Now in this case you can see the time period is high. Okay, here the discharging time period. This is the discharging time period. One case I have considered discharging time period, that is tau. If the discharging time period is high, that means your frequency is going to be less. Now if the frequency is going to be less, that means some of the part present in our AM signal is not considered. My envelope must touch peak to peak of each and every possible value. Peak to peak value with respect to this. You can see that each peak where it touches with respect to this envelope in lower side as well as upper side. But when this time period, when this discharging time period is high, that means your frequency is less. If the frequency is less, that means your modulating frequency must be greater than F. It must not be less than F, it must be greater than F. Here it is less than F. So if it is less than F, some of the modulated signal are not considered. It is not considering the envelope of this particular signal. So if this particular cases arises, that means we need to control the frequency. Now how we can control the frequency? We had a condition that it must not be, the FM must be greater than F and F must not be less than F. If it should be lies between these two conditions. So what is that condition? For proper envelope detection, 1 by Fc less than tau less than 1 by F1. So that means if this condition is satisfied, then we can recover the original modulating signal with the help of the envelope detection. These are the cases. So this is the case 1, this is case 2, if it is high, if it is small, and these are the cases through which we can recover our original modulated signal. Okay. Now here in the third, I will show the total construction of extracted modulated signal. I will write extracted signal. Extracted signal, after that output. So first, if we are satisfied this proper envelope detection, then how the output will look, let's see. Suppose this is the positive half we are considering. Okay, so this is first, this is second, this is third, fourth, fifth, sixth, like this. Now if it is satisfied this proper detection, now what will happen? First it charges, then it discharges, then it is charges, then it is discharges, then it is charges, discharges, charges, then it is discharges, and this is the discharges. Now this is the proper envelope detection. Here peak to peak value were identified, but in this case one of the peak was missing. Now this missing of information or missing of modulating signal in a modulated signal will hamper to reconstruct the original signal. Now when this signal is passed through a smoothing filter, okay, when it is passed through a smoothing filter, when it is passed through a smoothing filter, That smoothing filter means that RC. It will act as filter also, parallel component of RL and C. So output of this will be in this particular form. So this is your modulating signal. Okay. So this is the modulating signal. Now what is the advantage of envelope detection? The envelope detection advantage is it also indirectly identify the mode of operation. Now here you can see that my modulating signal is a cosine signal which starts with some DC offset value, and it indicates that if I will modulate this one, this modulating signal with a carrier, the modulated signal we will generate as MA is less than 1. Now there are the certain inputs and outputs are there that we will discuss, through which we can identify the modulation process. So this is the basic concept behind the operation of envelope detection. This envelope detection will help us to identify the presence of modulating signal in my modulated signal. Where it will identify? It will identify the presence of envelope. Which is the envelope? This is the envelope. Okay. So it is touches to the peak to peak. If it is satisfied, this condition. If it is not satisfied, these two cases will arise. In one, maximum dip will be there. The maximum means short signals will be generated. This is called, these particular things are the short signal will be generated, through which we cannot reconstruct our original signal. Similarly, if it is greater, if the time constant is high, frequency is less, we are going to miss some of the side lobes, some of the information, some of the peak of that amplitude modulated signal. If it is missing some amplitude modulated signal, we cannot reconstruct the original signal. So it must satisfy this particular condition, envelope detection condition. Okay. Now next we will see, if I am providing a modulating signal, then what will be the outputs of envelope detector? One by one we will see. Okay. Let me erase it. Okay. So now let us consider this is a device. Okay, that is envelope detector. Done. Now in this envelope detector, if I am providing certain cases, first, if my modulating signal, okay, if my modulating signal is like this. Now if my modulating signal is like this, then my modulated wave will look like this. Okay, after modulation, this sort of modulated signal will come. So this indicates what? this indicates that we are discussing about modulation index less than 1. So when this sort of AM signal we are providing, to the envelope detection, then what is the output? What is the condition for the envelope detection? The proper condition is 1 by Fc must be less than RL into C and must be less than 1 by F for proper envelope detection. If this condition is satisfied, then what will be the output of envelope detection? The output of envelope detection will be in which these are the output, positive half. Okay, and if this is the positive half we are identifying, that is output, that means first it will identify charge, then discharge, then charge, then discharge, then charge, then discharge, then charge, then discharge, then charge, and then discharge. So after passing through the smoothing filter, what will be my output? My output will be the message signal. The output will look like this. So this signal and this signal are quite similar. Yes, it is similar because it is following this particular condition. What is that condition? The proper envelope detection. 1 by Fc must be very less than the time constant, which is very less than 1 by Fm. Now this condition, if it is satisfied, I am recovering this modulating signal. Now from this output of a modulated signal, also you can decide in which modulation or which type of modulation it has been done. So it comes under your under modulation. That means MA is less than 1. Okay, and here we are getting only with respect to the magnitude, because the DC component, whatever the output of a diode, will act as a magnitude. Okay, so here the magnitude is our modulating signal. Okay, so here I will write what is input to the envelope detection or detector and output of envelope detector. Okay, so input of envelope detector is, let us consider sine signal. If it is sine omega t or cos omega t. If it is only cos and sine, then here we will get only the DC component, DC output. Why? Because in the previous session I have discussed, if I am providing the sinusoid signal, only the DC component we are identifying. If the cosine signal is given, the output will be in a DC form. For example, if this is the sine wave I am giving to the envelope detector, okay, my outputs will look like this. Means first it will discharge, first it will charge, and then it will discharge. First charge, then discharge, then charge, then discharge. Okay. Now if it is passing through a smooth filter, okay, if it is passing through a smooth filter, it will look like this. That means after certain amplitude, it will identify a constant output when the envelope detection is satisfied. If the proper envelope detection condition is satisfied. So this is the output. Similarly, if I am providing some cosine signal like this is the sinusoid signal, this is the cosine signal. If it is provided to the envelope detector, your output will have, so since it is starting from this, so your output will look like this. Okay, so this is your output of envelope detector. And the output of smoothing filter will be a DC. So simple, it is a DC output will be there. So this is the output of smoothing filter. Smoothing filter. This is also output of smoothing filters. Okay. So these are the cases for sine and cosine. If it is sine having a sin omega t or a cos omega t, it is peak value minus a plus a, this is also minus a plus a, then your output will look like this. Only the DC component is going to be available. Okay. Now next, if AM signal is provided to the envelope detector, what it means? Here as I have shown, if AM signal which is modulated with the modulation index less than A, its output is only the positive half, and if it is satisfying the proper envelope detection condition, then you can reconstruct the modulating signal. Okay. Similarly, the other case I will show. If my modulating signal is like this, if my modulating signal is touching to the zero crossing point, okay, touches to the zero crossing point. This is the modulating signal. Now, if the modulating signal is look like this, then what will be my carrier component or modulated signal? My modulated signal will be look like this. This indicates that, and your carriers are available here. Okay. This indicate what? This indicate for critical condition. Means MA is equals to 1. When it's MA equals to 1, then the amplitude of modulating signal and the amplitude of carrier is same. Then these particular AM modulated signals are generated. Okay. Now once this AM signal is generated, we need to extract the modulating signal. What I will do? I will provide this input to the envelope detection. Now envelope detection outputs we will see now. So first, due to the presence of diode, only the positive half is going to be extracted. So positive half is going to be extracted means, so this is the positive half. Okay. So here the cycles, half cycles are available. Okay. Half cycles are available. Now, if it is satisfied that proper envelope detection, charging, then discharging, then charging, then discharging, then charging, then discharging, charging, then discharging, charging, then discharging, this sort of signal will be output. Now, when this signal will pass through a smoothing filter, okay, when it is passed through a smoothing filter, we will reconstruct the original message signal like this. So this is the output of the smoothing filter, which is available in envelope detector. That smoothing filter is nothing but parallel combination of RC. Okay. So this is the output. So with the help of this particular scenario, this is for case 1, this is for case 2. Case 1, if the modulation index is less than 1. Case 2, if the modulation index is equal to 1. Now, then also we are getting the magnitude. Okay. So here, if I am providing the AM signal, AC 1 plus Ka M of t cos omega c. So this is the AM signal. Okay. Some of the book it will be written in terms of K, and in some of the book it will be written in terms of MA. Both are same. So it is AC 1 plus MA cos omega mt cos omega C. Now when this envelope is given, okay, so when this particular factor or this particular AM signal is provided to this envelope detection, then what will be the output? The outputs will be only the magnitude part. That means only the magnitude part. Let us consider this is my AM signal and the output is available with respect to the modulating signal. So modulating signal here is AC into KA into M of t. So if the A amplitude modulated signal is provided, that means my output is modulating signal. If the input is sinusoidal or cosine signal, the output is DC as I have shown. Similarly, if you provide the AM signal this, then your output is modulating signal. So this is your second condition. Okay. So second condition is this. That means what? If I am providing the modulated signal, my output is modulating signal. That I have written. Done. Now, third case, if my modulation index is greater than 1, what happens? So I will erase this one. Now this is M of. Now here, if MA is greater than 1, MA is greater than 1 means the magnitude of modulating signal is high with respect to the carrier component. So let us consider this is the modulating signal, and for this my modulated signal S suffix AM of t. Due to the over modulation, it will suffer envelope detection. Envelope means overlap of some distortion. Envelope distortion we will identify. So first, so this sort of envelope distortion we will identify. So this is the carrier component, and in this phase reversal will be there due to the envelope distortion. Okay. Now if this envelope distorted wave or the over modulated signal is provided to the envelope detector, then what will happen? Due to the presence of the diode, it will only identify the positive half. It will only identify the positive half, like this. Okay. So here my carriers are available, positive half carriers, and since due to the presence of that capacitor, it will charge, discharge, charge, discharge, charge, discharge, charge, discharge, charge, discharge, charge, discharge, charge, discharge. Now passing through this through a smoothing filter, we will get the output look like this. This is my output. So this is the output of which one? Output of envelope detector. Now the concept says any detector we are using, the output must be the message signal. Okay. Is this your message signal? No, it is not my message signal. So if it is not my message signal, that means what this envelope detector is doing? The envelope detector is work only for MA less than equal to 1. So that means the envelope detector work properly. It will reconstruct the modulating signal only for under modulation and critical modulation, not for this over modulation, because the output of this over modulation is different with respect to the input provided. In other cases we have seen that if the modulation index is less than 1, if the modulation index is equals to 1, the message signal we are reconstructing. But with the help or when we are transmitting the signal with over modulation, the reconstruction of modulating signal is very difficult. The different sort of outputs will come. What outputs? This is a distortion will come. Here it is not my message signal, it is a distorted component is available in the received modulated signal. Due to the presence of this envelope distortion, we are losing the presence of message signal. We are getting some information, but this information is not same as we are transmitting. So what is the advantage or what is the principle behind this envelope detector? The envelope detector perform well for under modulation case as well as for critical modulation case, not for this over modulation case. So for practically we are avoiding this over modulated signal transmission. Okay, so these are the small concepts behind your envelope detection. So in this I have jotted down, if the input signal is sine and cosine, then the DC components are available. So if it is a sine, this sort of DC will available. If it is a cosine, this DC signal will be available. Now if I am providing the AM signal, that too modulation index is less than equals to 1. If the less than equals to 1, then only we are extracting the modulating signal. But if it is greater than 1, we are losing the presence of modulating signal. So that we have seen with respect to this sort of figures, this sort of analogy. These questions in exam they will ask that why this envelope detection is not working properly for over modulation. That means you have to write all these concepts. For MA less than 1, MA equal to 1 and MA greater than 1. Okay. Next we will see the relationship or the modulated signal relationship between the time constant and the modulation index, because here as we are transmitting the information with a modulated process, okay, that modulation is done with respect to certain condition. What is that condition? Degree of modulation. Degree of modulation or depth of modulation. So when we are extracting this information, as you can see that modulation index is greater than 1, so what will happen? If it is less than 1, what will happen? If it is equal to 1, what will happen? That we have seen. But how we will identify those relations? What are the basic relations behind the modulation index with the time constant present in that RC filter? Okay, that we will discuss and then we will wind up. It is a small derivation. I will write the derivation for single tone modulating signal. Okay, so my AM signal will be AC whole into 1 plus KA M of T whole into cos omega c. So this is the single tone modulated signal. Now in this single tone modulated signal, my envelope, okay, my envelope will have only the magnitude part. This is called as your envelope. That is AC 1 plus KA M of T. Why I am using this envelope? Because this envelope is going to play a vital role while we are discussing about the time constant in the envelope detector. Okay. Next, envelope detector must be less than the slope of voltage drop across capacitor Vc of T. So with the help of this relation we can form an equation with respect to envelope detection and the slope of this one. The slope means the slope of Vc and this Vc of T, I will write dVc of T by dt is greater than slope of envelope detector. So slope of envelope detector means d by dt. So one by one you have to identify d by dt means you have to differentiate this, which must be greater, your voltage drop across capacitor must be greater than this particular value. If it is greater, then only the modulation index will be related with respect to the time constant Rc into L, because Vc is the voltage drop across capacitance. Okay, if the voltage drop across capacitance is greater than the slope or the voltage available in our envelope detector, then only we can extract the original modulating signal. So this is the condition which plays a vital role. So now, if we solve this, means magnitude of this must be greater than magnitude of this. So Vc of T, voltage drop across capacitor, is E into minus T by Rc. Now as we know that the capacitor voltage drop is with respect to exponentially decreasing. So it is exponentially decreasing with the time constant Rc. What is the voltage drop? Voltage drop is the envelope. So what is the envelope? What is the potential available in our modulated signal? Okay. So now if we expand it, 1 minus T by Rc, neglecting the higher component. If you expand this one exponential, it will be come in terms of factorials. 1 minus T by Rc plus 1 T by 2 factorial into Rc, like that it will come. I am neglecting the higher component, so it is T into T minus 1 by Rc. Next, so dVc of T by dt. I need to calculate this component dVc of T by dt. If you differentiate it, you will get minus T divided by RL into C. This is RL into C. Okay, RL into C. So minus T divided by RL into C, where dE by dt. Now we need to differentiate E. E is how much? E is AC whole into 1 plus, I will write MA cos omega mt. Okay. So now if you differentiate this, you will get minus AC into MA into omega m, presence of sine, cosine will become sine omega mt. So this is d by dt. Now this is my d by dt. This is my dVc of T by dt. Now you need to equate these two, because here the maximum value are this much. Okay. So now if you equate it, you will get E by RL into C must be greater than AC MA omega m sin omega mt. So this is the condition. So E by RL into C must be very greater than AC into MA omega m into sin omega mt. Now here you can see this RL is related with respect to modulation index. Your time constant is related with respect to modulation index. Okay. Now if it is related with respect to modulation index, how we are going to proceed? We are going to proceed 1 by RL into C is very greater than AC divided cancelled out. Now what will be the maximum value? The maximum value need to differentiate this one with respect to time. Then it will get the maximum value. So after differentiating the RHS, maximum value obtained. If the maximum value is obtained, we will get MA omega m root over of 1 minus MA square whole divided by 1 minus MA square whole divided by 1 minus MA square. So 1 by RL into C is equals to MA omega m 1 minus MA square divided by 1 minus MA square. So here I can write RL into C, take upside, you will get root over of 1 minus MA square divided by MA into omega m. So time constant is related with respect to modulation index. So this is the relationship between the time constant and the modulation index present in our modulated signal as well as the modulating frequency. With the help of these relations, we can identify the modulation index if we know the time constant. Okay. So these are the certain relations which will help us to identify the modulating signal if we are using the envelope detection. Okay. Thank you. Next class we will discuss about these relations, mathematical analysis.